May 18th, 1980, 8:32 on a Sunday morning in southwest Washington state. For 2 months, Mount St. Helens has been shaking. For 2 months, one side of the mountain has been swelling outward, a bulge on the north face growing at times by 5 feet a day, pushed from within by magma no one can see. Every scientist watching knows something is coming. None of them know it will come sideways. At 8:32, a magnitude 5 earthquake shudders through the mountain, and the entire north face, a slab of rock over a mile wide, breaks loose and begins to slide. It is the largest landslide in recorded history, and it uncorks the mountain like a thumb coming off a shaken bottle. What comes out does not go up, it goes out. A wall of superheated rock and gas, roughly 660 degrees, bursts sideways from the torn open flank and races north across the landscape at near the speed of sound. 6 miles away, on a ridge that the science of 1980 had marked as safe, a 30-year-old geologist named David Johnston sees it coming. He has just enough time for 5 words into his radio. "Vancouver! Vancouver! This is it!"
Vancouver! Vancouver! This is it!
In the next few minutes, that sideways blast will flatten 230 square miles of forest. It will strip 1,000 feet off the top of the mountain, and it will kill 57 people, most of them, like Johnston, standing in places that had been declared outside the danger zone. This is the story of how the deadliest volcanic eruption in American history killed almost no one the way anyone expected. Because the mountain didn't explode upward, it exploded sideways. And nobody, not even the scientists with their instruments bolted to its flank, had believed it could. To understand why May 18th unfolded the way it did, you have to go back to the 2 months before, to the warnings the mountain gave, the line drawn on a map, and the single assumption that got almost everything wrong. For 123 years, Mount St. Helens had been quiet. To the people of Southwest Washington, it wasn't a threat. It was the postcard, a near-perfect snow-capped cone, the Fuji of America, reflected in the still water of Spirit Lake at its foot. Cabins lined the shore. Loggers worked its flanks. It was scenery, not danger. Then, in March of 1980, the mountain woke up. It began with earthquakes, a swarm of them, small at first, then steadily larger and more frequent, clustering directly beneath the peak. Within a week, the shaking was intense enough that scientists from the U.S. Geological Survey converged on the mountain. On March 27th, St. Helens gave its first outward sign. A burst of steam blew a new crater through the summit ice. Over the following weeks, the summit cracked open further, and small explosions of steam and old rock became almost routine. The mountain was clearing its throat, but the steam was not the thing that frightened the geologists. It was what was happening to the shape of the mountain itself. On the north flank, the ground was beginning to swell. Measured carefully, week after week, the bulge was found to be growing outward, at its fastest, by as much as 5 feet a day. Something beneath the surface was pushing the entire north face of the mountain outward, and it was doing it fast. This was magma, rising into the volcano and collecting just beneath the flank, inflating it from the inside like a blister. It is worth being precise about how fast 5 feet a day actually is, because the number is easy to skim past. Mountains are the slowest things most people can name. We use them as the very symbol of permanence and deep time. A mountainside that moves a measurable, visible distance every single day is not a mountain behaving like a mountain. It is a structure in the process of failing on a human timescale in front of the instruments. Geologists could set up a survey point in the morning and watch it be measurably farther away by the next. That is what alarmed them more than any single earthquake. Not that the mountain was shaking, but that a piece of it the size of a small city was visibly, steadily walking outward into the air, held back by nothing but its own crumbling rock. By May, the bulge extended more than a mile across and had pushed the north face outward by hundreds of feet. To the scientists watching it, the meaning was unmistakable and deeply alarming. The mountain was becoming dangerously, structurally unstable. A slope can only be pushed so far before it fails. What no one could agree on was exactly when it would go, or precisely what would happen when it did. This is the kind of story this channel exists for, the disaster told properly, from the inside. If that's why you're here, subscribe, and the next one finds you. As the bulge grew, a hard question landed on the authorities. How far back do you push people? This is where the human story of May 18th is really decided. Not in the eruption itself, but in the weeks before, in the drawing of a boundary. Officials established restricted zones around the mountain, keeping the public back from the summit. But the zones were a negotiation, not a clean scientific verdict. There was enormous pressure. Property owners wanted access to their cabins. Logging companies wanted their crews working. The precise reach of a possible eruption was genuinely uncertain. No one alive had seen this mountain erupt. And so, the danger zone was drawn as a compromise between the science, the economics, and the politics. The critical, fatal assumption baked into that map was simple: that a volcano erupts upward. The models, the boundaries, the sense of what was far enough, all of it quietly assumed that the danger radiated from the summit and rained down from above. Get far enough from the crater, stay out of the obvious blast-up zone, and you were considered safe. David Johnston's observation post, Coldwater 2, sat about 6 miles north of the summit, outside the line, on ground judged survivable. Johnston himself was one of the few who sensed the map might be wrong. He understood the bulge for what it was, a loaded, unstable slope pointed north, and he'd reportedly described standing near the mountain as standing next to a stick of dynamite with the fuse lit. He knew it was dangerous. Even he did not know it would come sideways and reach him where he stood. There's a detail here that captures the whole impossible position the authorities were in. In the weeks before the eruption, the restricted zone became a genuine flashpoint. Cabin owners, furious at being kept from their property on a mountain that had done nothing but steam, organized and pushed to be let back in. A convoy of property owners was actually escorted up to retrieve belongings in the days before May 18th, and a second trip was scheduled for the morning of May 18th itself. Had the mountain waited a few more hours, that convoy would have been on its flanks when it failed. The line on the map was not just a scientific estimate. It was under constant, organized pressure to be moved inward, closer to a mountain that every instrument said was becoming more dangerous by the day. The people drawing it were balancing physics against property rights, with no precedent to point to and a public that could see only a quiet, pretty mountain. The warnings, in other words, were not absent. The mountain had shaken for 2 months. It had grown a visible, measured deformity, a mile wide. The scientists had said clearly that it was unstable and dangerous. What failed was not the detection. It was the imagination, the inability to picture that all of that stored energy might not go up, but out. The signs were red. The direction was not. To understand why Mount St. Helens exploded sideways, you have to understand what the bulge actually was, and what was trapped behind it. A typical volcanic eruption is, in the simplest terms, a pressure release valve pointed at the sky. Magma rises up a central conduit, gas comes out of solution as the pressure drops, and the whole mixture blasts upward out of the summit vent. The mountain vents through its top. That is the picture the 1980 danger map was built on. But St. Helens in May of 1980 was not set up that way. The magma rising into the mountain had not reached the summit vent. It had stalled in the north flank, forming what geologists call a cryptodome, a body of fresh, gas-charged magma trapped inside the side of the mountain, unable to break the surface. It was under immense pressure, and the only thing holding it in was the rock of the north face itself. The very slope that was bulging outward, growing more fragile by the day. Picture a bottle of champagne, warm and shaken, with the cork jammed in sideways. The pressure isn't pointed up. It's pointed at the weakest wall. At 8:32 that morning, that wall failed. The magnitude 5 earthquake shook the oversteepened north face loose, and a full cubic mile of the mountain detached and began to slide as a single, colossal mass. This is the part people miss. The landslide came first. And the landslide is what turned an eruption into a catastrophe. Because the instant that slab of rock slid away, it removed the lid that had been holding the pressurized cryptodome inside the mountain. The effect was near instant, and it has a name: decompression. Take the confining weight off a body of gas-charged magma suddenly, and the dissolved gases flash out of solution all at once. The same physics as a shaken bottle uncorked, scaled up to a mountain. The trapped cryptodome, freed of its lid, detonated laterally through the gap the landslide had opened. Not upward, sideways, in the exact direction the slope had failed. North, toward Coldwater 2, toward Spirit Lake, toward David Johnston. To grasp the scale of the energy released, consider what decompression actually does at these pressures. The gas dissolved in magma behaves like the carbon dioxide in a sealed bottle, invisible, held in solution by pressure alone. As long as the lid is on, it stays dissolved and quiet. Remove the lid, and it doesn't leak out gently. It comes out of solution explosively, expanding by hundreds of times its dissolved volume in a fraction of a second, shredding the magma around it into a high-speed spray of rock and gas. Now scale that from a bottle to a body of magma the size of a hill, buried in the flank of a mountain, and release it not through a small opening, but through the entire raw wound left by a cubic mile of vanished slope. The blast that resulted was not a jet. It was an expanding wall, a pyroclastic density current, hugging the ground and accelerating across it, faster than the landslide that had triggered it, overtaking and outrunning the very avalanche that had uncorked it. And the sequence matters, because it is the key to the whole disaster, and it is the part almost everyone gets backwards. The landslide did not come after the eruption. It came first, and it caused the eruption. The earthquake shook the oversteepened slope loose. The slope's collapse removed the confining pressure, and only then, in the seconds that followed, did the decompressed cryptodome detonate through the gap. 3 events in a chain, in the right order, in a matter of seconds. Earthquake, then landslide, then lateral blast. Change the order, and you do not get May 18th. It was the collapse first sequence that aimed the explosion sideways. This is why May 18th broke every assumption. The danger was never really the summit. It was the direction the mountain chose to fail, and a failing slope points its blast wherever it collapses. The map had drawn a circle around the peak. The mountain drew a line and fired along it. What came out of that gap moved faster than almost anyone could comprehend. The lateral blast, a scorching cloud of pulverized rock, ash, and volcanic gas, burst from the north face at an estimated temperature of around 660 degrees Fahrenheit. It expanded across the landscape at speeds that reached, at their peak, close to the speed of sound. Ahead of it, a shockwave. Behind it, total devastation. In the span of a few minutes, the blast swept out across 230 square miles. The zone closest to the mountain was scoured to bare gray earth, everything erased. Beyond that, across a vast arc of forest, the effect was even more haunting. Entire hillsides of mature, old-growth trees, some of them centuries old, were snapped off at the base and laid down flat, all pointing away from the mountain in perfect parallel rows, like matchsticks combed by a giant hand. 230 square miles of standing forest, flattened in minutes. The landslide itself, the largest in recorded history, poured down the north flank and into the valley of the North Fork Toutle River, burying it under an average of 150 feet of rock and debris in places far deeper. Part of it slammed into Spirit Lake, displacing the water and raising the lake bed hundreds of feet. Only after all of this did the eruption finally do the thing everyone had expected in the first place. It went vertical. A column of ash surged upward more than 15 miles into the sky, and for the next 9 hours, the mountain poured out a plume that turned day into night across eastern Washington. Ash fell like gray snow. In towns hundreds of miles away, streetlights came on at noon. But by the time that ash column climbed, the people the eruption would kill were, almost all of them, already gone, taken not by the ash from above, but by the wall of heat that had come sideways in the very first minutes. When it was over, the mountain was a different shape. The graceful cone was gone. In its place, a gaping, mile-wide horseshoe crater opened to the north, its summit blown and slid away. Mount St. Helens had lost roughly 1,300 feet of height in a single morning, from 9,677 feet down to 8,363. To understand why Mount St. Helens was capable of this, and why it will be again, you have to know what kind of mountain it is. The Pacific Northwest sits above one of the planet's great collision zones. Off the coast of Washington and Oregon, a slab of the ocean floor, the Juan de Fuca Plate, is grinding slowly beneath the edge of North America, diving down into the hot mantle below. As that slab descends, it releases water into the rock above it, and that water lowers the melting point of the mantle, generating magma that rises toward the surface.
It rises.
This is the engine behind the entire Cascade Range, a line of volcanoes running from British Columbia down through Washington, Oregon, and into California. Mount Rainier, Mount Hood, Mount Shasta, Mount St. Helens, they are all children of the same subducting slab. But St. Helens is a specific and dangerous kind of cascade volcano. Its magma is rich in silica, thick, sticky, and full of dissolved gas. Thin, runny magma, like Hawaii's, lets its gas escape gently. It produces rivers of lava, not explosions. Thick, gas-charged magma, like St. Helens, does the opposite. It traps its gas until the pressure becomes catastrophic, and then releases it all at once. This is why St. Helens doesn't ooze, it detonates. and it is also the youngest and most frequently active volcano in the Cascades. Over the last several thousand years, it has been the one most likely to erupt, and to erupt violently. The 1980 eruption was not an aberration for this mountain. It was the mountain being exactly what it is, which reframes the postcard. The near-perfect cone that people photographed in Spirit Lake before 1980 was not a symbol of permanence at all. That elegant symmetry was itself the product of repeated violent eruptions building the cone up, layer by layer, over just a few thousand years. A geologically brand new mountain, assembled by exactly the kind of event that destroyed it. It had been beautiful because it was dangerous. The two were never separate. If you're still here, you're exactly who this channel is built for. Subscribing takes 2 seconds, and it's the whole reason these keep getting made. 57 people died on the morning of May 18th. Almost none of them were where anyone would have called reckless. Most were outside the official danger zone. The first name most people learn is David Johnston. 30 years old, a volcanologist with the USGS, he had drawn a shift at the observation post 6 miles north of the summit, Coldwater 2, a spot on ground the map called safe. He was one of the scientists who best understood how dangerous the bulge was, and he had argued to keep the public back. When the north face failed and the blast came north, he was directly in its path, with seconds of warning.
Vancouver! Vancouver! This is it!
His final radio call, "Vancouver! Vancouver! This is it!" reached the monitoring center in those first moments. Then the transmission ended. His body was never found. He had been right about the danger, and standing exactly where the science of the day had promised he'd be fine. He was not alone on that side of the mountain. There was the man who had refused to leave the lodge he'd run for decades on the shore of Spirit Lake. An 83-year-old innkeeper who had become, in the weeks before, a folk figure for his stubborn insistence that the mountain wouldn't dare take him. When the blast came, the lake and everything on it vanished beneath the debris. He was never found either. There were photographers drawn by the once-in-a-lifetime chance to document a waking volcano caught in the blast zone with their cameras. Some of their final frames survived even though they did not. There were loggers who happened to be working the forests that Sunday. There were campers and sightseers on roads and ridges that felt like a comfortable distance from a mountain that had, until that morning, only ever puffed steam. Families waiting to hear from people who had driven up for the weekend to see the famous shaking mountain would learn, over the following days, that the ground those people had been standing on no longer existed. The blast did not kill at random, but it did not kill by the map either. It killed along a direction, the arc the mountain fired into when its north face gave way. Whether you lived or died on May 18th came down, more than anything, to which side of the mountain you were on, and whether you were standing in the path the collapse happened to open. Not distance from the summit, direction from the wound. The eruption of May 18th, 1980, remains the deadliest and most economically destructive volcanic event in the history of the United States. But like the disasters this channel keeps returning to, its real legacy is not the destruction. It's what the destruction forced people to finally understand. Before St. Helens, the lateral blast was a phenomenon volcanologists knew could happen in theory, but had never watched unfold with modern instruments trained on it. May 18th changed that overnight. The eruption became one of the most closely studied volcanic events in history. and the concept of the directed blast, the sideways eruption driven by flank collapse and decompression, moved from a footnote to a central danger that hazard maps around the world now account for. Volcanoes from Washington to Japan to the Andes were reassessed with a new question in mind. Not just how high could this one erupt, but which way could it fail? The line on the 1980 map had assumed up. Every serious map drawn since has had to ask, which direction? There was also a second act to the disaster that unfolded over years, not minutes. The landslide had dammed the valleys and choked the rivers with debris. For years afterward, the threat was water. The risk that a debris dam holding back a newly formed lake could fail and send a wall of mud downstream toward towns. Engineers eventually had to bore a tunnel through solid rock to drain Spirit Lake and relieve the pressure. A slow-motion emergency that outlasted the eruption itself by a decade. This is a pattern worth noticing across these disasters. The initial event is over in minutes, but the landscape it leaves behind stays dangerous for a generation. And then, slowly, life returned, faster than anyone predicted. Within years, the gray wasteland the blast had scoured began to green again, colonized first by fireweed and burrowing animals that had survived underground, then by returning forest. The blast zone became one of the most important natural laboratories on Earth for understanding how ecosystems recover from catastrophe. The mountain that had erased life across 230 square miles became the place scientists went to watch life come back. Mount St. Helens itself did not go back to sleep. Through the 1980s, it slowly rebuilt, extruding thick lava that piled into a dome inside the new crater. It stirred again between 2004 and 2008, building more dome, monitored the entire way. And it is, quietly, still an active volcano today, its plumbing intact, its reservoir still there beneath the horseshoe crater, still recharging on a timescale measured in decades. Which is the part that should stay with you. The mountain that erased 230 square miles in a single morning is not a closed chapter of history. It is a living system that is, right now, doing the slow underground work that eruptions are built from. And the great lesson of 1980, that the danger is not always where the map says that a volcano can fail in a direction no one expected, is not a lesson about the past. It is a standing warning about every quiet, beautiful, snow-capped mountain that has not erupted yet. Because here's what almost no one realizes. Mount St. Helens is shaking again right now, and it's doing something that, on its face, makes no sense at all. That's the next story. Subscribe, and it'll be waiting for you.